presentation about. Thank you for joining my presentation. And this is about how to work with PhysiCell data in Python. And it's mainly a tool called PhysiCell Data Loader. And in earlier days, this was called Python Loader. And it was a little bit further developed, and I will show how I use it to analyze data in Python and hope to inspire you to do maybe the same. So how should you understand this PhysiCell Data Loader? Actually, I think the best way to look at it is it should be kind of the USB port to PhysiCell. And as we started further to develop last year on this Python library, there were some major points that we really want to focus on. So it should be as much backward compatible as it was possible, because somehow the community was used to use this tool, and we didn't want to break with the habits. Then, of course, as always for us, it has to be platform independent, so it has to work on Windows, Mac, and Linux. And then the request that I had to the tools was that it's pip installable, because the old loader wasn't pip installable, and so that this had some burden with it, and I tried to resolve these burdens. And I had really the idea to develop it so further that it's really loading PhysiCell output data into Python 3, and then I supply this loaded data in well-established format so that it can be used from other software. And to phrase it in a different way, we really not try to be analysis software. We try to be the default connector between PhysiCell output and analysis software. And if you write an analysis package, then maybe it's great, and we will try this with some of the existing analysis packages to put PCDL in, that it acts as the interface from loading the data from the output folder and being used from there. But what I now will focus in this presentation is that we just use the PhysiCell Data Loader in the Python REPL and really analyze data ad hoc and on the fly. And so we'll see in this presentation how far we get on this. So from the blueprint, what the library itself does, each time step that we have from the modeling is called an MCDS time step, so multicellular data standard. And one of these MCDS objects or time step is in Python packed into a dictionary. Actually, it's a dictionary of dictionary, and it has a well-defined structure. We have changed it a little bit from the original version. And the major thing is that we have functions, and through this function, we can really access all of this data. So in big part, you will maybe never have to do with this underlying data structure. You can just use the functions, but it's maybe just good to know how the blueprint looks like. And we see we have a dictionary inside for the metadata. We have a dictionary for the mesh, and we have a dictionary for the continuum variables, which are the substrates that we have, like oxygen. And we have as well a dictionary for the discrete data, so our agents. And yeah. So if you were really interested to learn more about everything about PhysiCell Data Loader, there is a README, and it links to several subpages. So there's a how-to guide, mainly focusing on how to install it. Then there is a tutorial who really goes through each of the available functions with an example. There is as well a test data set that it directly can run everything that you find in the tutorial. It's a little bit strange test data set. I use this for doing unit tests on the software. So it's really just that you have an impression what goes on. It's not really a data set that is there for analysis, but it's just handy that you can run the tutorial with it. And then there's a reference manual who as well lists each of the possible commands, and I as well highlighted which of these commands are important for data analysis. I call them workhorse function. There are a lot of other functions, and they're important for people who build software, and they're as well maybe important for historical reasons, so they will stay there. Just that you know why there are so many commands. And then there will be a discussion part. Soon we publish the software, and hopefully sooner than later. So the dependencies that PC Data Loader has. So as I said, it's pip installable, and when you just want to have any dependency, you just can write pip install pcdl square bracket all square bracket closed, and it will just install any dependency. But if you focusing on lightweight installation that really can just do the basics and not uses what we later will learn about the OnData project, then you can just do pip install pcdl. And this has only matplotlib, numpy, pandas, and scipy dependencies, and this is usually always loaded when you do data analysis with Python. So it's very lightweight. And when you have software that you want to implement on top, this is maybe the way how you should use it as a dependency. Then when you want to do data analysis, what we see now in this presentation, then you maybe better install with pip install pcdl scverse. This is for single cell universe, and we will learn more about this down the line. Or if you not want to do this all installation, what the all installation does, it does as well install this request library. This is pip install pcdl data, and this is used to download this test data for when you want to run the tutorial. So you can really tailor which dependency you really want to install. That was as well important for having it as a USB stick type of. So these are the workhorse functions that I mentioned, and don't expect you that you can read them, but these are the functions that are listed on the reference page. I just copy paste them out from there, and these are the functions we will step to now in the Jupyter notebook. So these were the ones from the time step, and there is another class that's a time series. So all the time step that you have from one PhysiCell run. Okay, so we come to the live demo. I know that all of you have installed Jupyter. I use Jupyter Lab. You can as well use Jupyter Notebook in itself. Jupyter Lab have the notebooks inside, but the handy thing is that you here as well see your folder structure, and it's just a little bit more comfortable interface, but it's all the same. So it's really just your taste. So before, I don't know if everybody was here, but you can download this notebook from our Git repo from the workshop, and here are the pip commands to install the required libraries for running this notebook. So PCDL, as told before, and ScanPy, and we use as well Leiden clustering in this notebook, and then SquidPy, which is spatial data analysis. It comes up later. Then when you copy this notebook into your PhysiCell folder, when you uncomment this one, these are just the usual commands that you run we run the interaction sample project that's the data that we analyze. And then there is really at the end, this is some three-dimensional example how to analyze three-dimensional data. And this is the Cancer Moon sample project. That is three-dimensional, and it only will process the first 24 hours, but it will take still an hour or it took an hour on my laptop. So you maybe shouldn't run this right now. The other one takes about 10 minutes. So if you might catch up if you want to follow, and otherwise, please just listen and do it later. So these are the libraries, the other libraries from Python that we will load. So most of them are installed, but these are the ones that we will analyze. And I already have the folders that automatically will be generated when you generate the data. And PCDL tells you as well that this is the latest version that was just deployed some hours ago. So 3.2.11. So you need this one to really run this notebook. Now, when I show this notebook, I will really use the time to explain how I do what I call REPL programming. And because for some people this might be new, for other people not. For them it's maybe a bit boring. Feel free to do what you want. But first, I really would like to show how I interact with my Python interpreter, and then down the road I will go faster to really show what the possibilities from these PhysiCell libraries are. So first we just load this 2D time series that we processed, and so this is the command. So before we have imported PhysiCell Data Loader, and now we use this PhysiCell Data Loader time series class to load it, and we load it into this variable, which called MCDS time step. That's the abbreviation that I have chosen. And you can see that it loads down each of the MCDS, or up more than down. And then, yeah, I make this a bit smaller. You don't see it more. Just a second, where am I? Sorry. Okay, yeah. Okay, I just close it because, I mean, you can see in the end, it looks all the same. I think this one the end. So it's just in the end, it says done, and then it's done. And so what I do when I really analyze data in the REPL, then I know the commands that I want to, but you forget about all the parameter settings. So the help command is very, very important. It's like when you're a little bit used to Linux, there are these man pages. And in the beginning, it's very strange, but at one point you realize it's very, very cool if you always have your documentation at hand and you can just write man and then which command to see the user manual and see listed your parameters. And it's the same with this question mark, or you could as well write help bracket and the name. So just want to show these two. So this one will be the same as the question mark. So it's a little bit rendered differently, but so when we in this first step, we want to generate images from the agents. And as you can see, we have here information about each of the parameters that we could set possibly to make, to run and get these images. And then there is another command to generate movies. Actually, there was a question yesterday where we could get more information. And it's always same structure. You have the input here. You have all the parameters that can be your input, and you have the output. So you know what you will generate, an MP4 movie in this case, and you have a little description what the function does. And this should give you enough information to understand what you have to enter. And we will as well use the function to generate GIFs. And those three functions, they are a little bit further developed, but they were already available in the PhysiCell make file. Usually you had the CSV generated, and from this one you could generate JPEG images, and from the JPEG images you could generate GIFs or movies, MP4 movies. And when you had a lot of time steps, it was a little bit slow, and it can be much faster done in Python. So I re-implemented this function in a little bit more versatile way in PC Data Loader. And this is now on the border from being just an interface. What my original plan was, this is already a little bit analysis, but because it was already in PhysiCell itself, in the make file, I think that is as far as I want to go to really implement analysis. I don't want to implement more in this model, but yeah. So I think I want to show how to run it. See, so we have the part, and we run these make image cells, and if you don't give any parameter settings, it will just make image cells from your cell type. And it will automatically, from the files that are around, there is always an initial SVG around. It will automatically generate read out how big the image will be, and will find some values that are kind of okay. So you're not, if you really just want to see the cell types, you don't have to give any specifics there. And as you can see, the output from this function is actually pad. And when we go up into our output 2 folder, then we see that it has actually generated these images, and it gives automatically always the name cell, because we at the moment use this image cell function and not the image sub function that we will for substrate that we later will use. And we go to the Z-spline 0 because it's 2D sample. So it automatically generates this folder name, and we visualize the cell types. And if you want to visualize something else like pressure or whatever, this name will change. Inside this folder, you find all the JPEG images. Nice thing on Jupyter Lab directly pops up here. Right. So now it gives a path back, as I said before. And the cool thing is that we can use this path to actually, we don't need this anymore, to make movies, MP4 movie, and we can as well use the path to make actually a GIF. So this takes a while. Hopefully it breaks. Yeah. So it should now generate the MP4 movie. And yeah, so this is the MP4 movie. And it should as well generate, not the MP4 movie again, but as well should generate the GIF file. So it's problem on the MP4 movie. I like MP4 movies, but in Jupyter Lab, you cannot see MP4 movie. Yes. So that's why I, in this notebook, more produce GIF files. But GIF files have another problem. When you have a lot of time steps, you will not be able to produce a GIF. Then an MP4 movie will be generated easily, but the GIF will cause problems. So let me see. Here's the GIF. And the nice thing is we can directly look at these GIFs here in Jupyter Lab. So once again, so this is the cell type, right? It's just a standard that we always look at. But of course, we maybe don't like the color. Really, this is the standard, so we want to have something more like color map auto. And a lot of these CMAP and so abbreviations are taken from pandas. So when you know pandas, you might, or Matplotlib, you might know some of these parameters, you nearly can guess them. So I regenerate now this GIF, movie it up. And then you will see that actually that it will change the color, but if you not delete it out from this tab here in Jupyter Lab, then you will not see that it have a new color. This one is still the old actually, but soon we have the one that have yes, turbo color. So we have or not. Yeah, great. I don't know when work. Maybe I was generating the movie. No, I don't know why it not works. I think it doesn't work because of that. Is it still running? Yes, it's still running. So it will generate a new GIF and then it will be right because I run it twice. I didn't comment it out before. Well, okay, it will just have different colors. I think it's not too exciting. We go on because of time. So here I run actually through two versions of generating images. So there's this image cell version, which is agent based, right? But there's as well this image subversion, which we can generate, for example, oxygen. So actually, I have to little thing to explain before. Okay, give me a sec. So here's a command, another command that is used that I first have to explain. Okay. So there is another function in PCDL that in the time series classes that you can, it's now the moment generating, that you can see a list of all the MCDS objects in a chronological order that were processed. Okay. This is the list from all the images that were processed. And of course, you can access them. It's a list, right? You can say, I want to have the first time step, for example. And that's what we here do. And then this is kind of, you can use all the functions that are around for this, for an MCDS object. So you can get here, what was I doing? Get substrate names, so get all the substrate names that are around, and this is actually in this sample, I think it's only oxygen. Okay, so no, actually, I'm in the wrong, my method is wrong. So there's debris, inflammatory, and quorum, and resources, and toxin that is around there. And I could loop over all of them, and one thing that I really want to show here is we generated two GIFs. One of them is now, this is a cell type seal. Sorry, I didn't want to show that. So we generated the debris, and we generated actually the debris as agents. So you see the level of debris surrounding directly that agent. And this is different than we are usually looking at this, but we have generated this too. So we have as well this substrate debris. So the GIF is here. So this is the usually one that you know where you have the contour plots. And you can see this is totally the same. So one shows you kind of the agent level of how your substrate is processed, and the other one shows you the usual contour plot level. And I think both of these plots are very useful. So the point I want to make, each of your substrate is as well available in your cell data frame. Just good to know, and that you can analyze this on a cell level too. Good. I see that time is running very fast, and I have to speed this up quite a bit. So, okay. And so I'm gonna now just quickly talk about the functions, otherwise we will not see anything. So this is a function to actually look about which states are there, and you can generate JSON files to see actually each of your feature and how many different value this feature has. And this is a nice function because you can actually say if over the whole time series, the value never changes. If I have no variation, then this feature is just not interesting because it has no information for this run. So you just kind of, you see I have 172 features. And when we now go to this JSON file here, can as well open them here, then you see a lot of these features have just one item. Here is one with 9, right? So this is more interesting because we have a density that have 9 different values in the whole time series. And there are features with thousands of values, right? Direction or so, but there are really a lot of features who only have one state. And when we want to analyze the data, we just want to get rid of those. So what we can do is that we set this state equals 2, and you can study the help function no more. Also go now, could look at the help function, and you would have information about that. but you can see what happens as well when I quickly put this in here. Yeah, just as an example. And this should now give back much less. Okay. So see, now we have 79. So we got rid of 100 features that just have no information. And we have the same for the cell data frame, and we have the same for the concentration data frame, which is the substrate, right? So now this was now all pandas-based kind of what we do there. We work with the data frame, but there is as well a new object that's called OnData object. And if you are from the wet lab, you maybe heard about that. This is the basic standard for doing single cell analysis, NRSeq analysis, or as well other single cell data. And the nice thing is now with we wrote a function that really transforms everything from PhysiCell into this, or everything, the thing they could do into this OnData object, and now you can analyze it as you would like analyze wet lab data. If this is new to you, still take the time to learn it, how to analyze data with OnData object, because if you ever have your hand at wet lab data, you will not have to learn anything new. You just can do the same because the functions are the same. So this is how you actually generate such an OnData object. And I take now the whole time series and I just write get OnData, and I get actually one single file back. Right. Still. And so I get one single OnData object back, and that looks like this. So it has 130 cells over the whole 130,000 cells over the whole time series, and it has 168 features. It has here some additional features. So these are numerical features. These are actually features that are categorical, and it has as well some spatial information. And you can as well, like MCDS, you can as well not you can as well not collapse it. This is the other way to do it. So then you get this list of OnData objects that was when you set collapse false. So this is two ways to generate these OnData objects. Okay, time is really running away. So I think I will just talk about most of the things, and then you have to work yourself through this notebook and maybe through a tutorial to really understand what's going on. So there is as well a way to get a time step. We have this PCDL time step function, and you can directly do it like you with giving the XML output file, but of course you can as well access it from the list. The problem is when you use this get MCDS list, then it will give you back an MCDS object that is actually from the pre-MCDS class, and this one have not a get OnData function. And this is done if somebody want to have the lightweight version installed. So if you really want to get the OnData function, then you have to use the get on MCDS list if you want to do it that way. But you can always use the PCDL.time series version, and then you have the right one. This is a little bit tricky, but I didn't see another way to solve this. Okay, let's quickly look at this time step. And now let's take 5 minutes to go through the Panda functions that are available, and then another maybe 10 minutes to look a little bit at OnData objects. So when you have worked before with PC Data Loader, something should be familiar that you get data frames and series back. So, and that's exactly what we do here. We have this get cell data frame. We have here state set to 1. We can set it to 2, right? If you anyway want to have only the one that uses information. And we get these data frames back. Okay. Then we can do the same for the substrate with this get concentration function. can look at the substrate names, you can get the info about, these are not so many substrates. And the nice thing is really that all of the substrates are as well in this get cell data frame, but they are on a cell level. Here they are on a voxel level or on the mesh level. So that's different from those data frames. Yeah, and then there's a function if you forgot about which units you used, so you can see each of the feature and which unit that it uses. Okay, but yeah, the OnData object, get OnData object is as well working on a time step level, not only on a time series level. And if you do heavy analysis with this object, it's good to know that you can save this object as H5AD file, and you can load it. So if you do spend half a day in analysis, you maybe want to save the object because it will store all of the processing that you did while you did your analysis. Let me see. Of course, I have first to load an object. Let's see. Okay. 1 second. Yeah. So this is time step that I have loaded, and I make the OnData object out of it here. Yeah. This is now from one single time step. And as we said before, this is what an OnData object is. Actually, when this is totally new to you, I recommend you to go to this home page. It's here. Oops, can you see this hopefully? It's here described as well. So you have here your data, you have here variables, which are more or less genes, and you have observation, which more or less are cells. But for us on PhysiCell, it turns out that the variables are just your numerical features, and the observations are your categorical features. But then, yeah, it's worth to check out this page. Oops, can I put this back? This, nah, whatever. Got it. Okay, good.
Elmar?
Yeah.
Do you have time for a question? I don't actually know the answer.
Yeah.
Great, I'll read it out loud. It's where would the user parameter data be stored in PC Data Loader? Also in this JSON file?
Say again, which parameter?
And the user parameter data.
It's all the user parameter data. So you mean the custom data, most probably. Custom data?
So, that's not the question. That's not the question that was specifically asked, but perhaps it's either. So where would, in general, where would the kind of, let's say, custom data or user parameter data be stored?
So I think the user parameter data, I'm not sure if the user parameter data is stored actually. I know that I deal with it, and I know that I solved the problem. And I have an answer for that. I have to go back, but the custom data, all these variables are stored, and they are actually in the data frames, and they are in the end data. And if it is numerical, then it should go into the numerical block. And if it's categorical, then it should go in the observation block, right? And the problem is that when you do custom data, you don't define what type it is. And when you run actually the load function, the time series or time step function, then it just assumes always it's numerical. But there is a parameter that calls type or so. You have to read the docs thing. And there you can, in a dictionary, specify each of your custom parameter and which type it is. Just say it's either string or Boolean or integer or float, and it will automatically put it to the right place from your pandas, from the OnData object. And yeah, the pandas not different, doesn't matter, but in the OnData object. And actually Boolean, I can as well quickly say this one, Boolean are treated as numerical data. So they're translated to integer and then the floats. So you'll find the Boolean there.
Okay.
And one thing as well, so you see the scale. So there are different ways to scale the data. And when you have gene expression data, this is different to our data. They usually log transform and look that you have kind of normal distributed data and all the log2 transformation so that people will know who come from the field. But for us, it's important that no value is just much, much higher than the other one. So I usually use this max upscaler, and this scales everything between -1 and 1. And there is as well a min max scaler, which will scale everything between 0 and 1. There's 3 different scalers there. And if you not want to do any scaling, if you want the raw data and scale it yourself in Random Project, you can do this as well. So this is just parameter settings from the get on data function. Okay, I have 10 minutes left. Should I just keep on going as far as I can? So these are the pandas plots. So, and as well, here we can look at the help function. And more or less, they have a line bar, horizontal bar, histogram box plot, KD, kernel density estimation, area pi, scatter, hex bin plot. And all of them, and this is now what I think about rapid programming, are accessible because we have data frames. So more or less, and here and now go really quick, you can take your data. I always take the cell type. You can do just a simple bar plot with the one-liner. You can do a horizontal bar plot with the one-liner. When you actually use, when you have a series, it will not give you a legend. When you have a data frame, it will give you a legend. You can do pie charts if it's Pi Day or so, and you have to celebrate. And you can go here for these are histogram. It's a histogram. Actually, this is now a series. That's why it isn't a legend. I don't like on this histogram that it does count. And here is a way, and these are a little bit more. These are 4 lines. It's not a one-liner, but when you look at this one, then we have the probability. So 80% probability that you are in this bar. So it's just plotting with pandas, and it's kind of useful to know which plots are around. Then same story, right? You can do kernel density estimation. So this tells all the same. If you do a histogram, if you do kernel density estimation, if you do a pie chart, it's all the same, just a little bit different flavor. And as well, box plot is kind of the same, but just turned around. So yeah, you know all of these plots, I'm sure. So then, of course, scatter plot is a big thing. The problem is when we do a scatter plot, we have no information about which cell type it is. And in these lines here, I actually color this one, and then I actually make here a legend, and I add actually the legend down in, at this moment, the lower left corner. And when you run it like this, then of course it doesn't work. Damn. For whatever reason, I don't know. Yeah. Okay, cannot tell. Oh yeah. Oh, shows this one, but this one is now the one, the colored one, and it has the legend here. But as you can see, it's quite awful when you have to do, if we really just the interface that I said, if PhysiCell is just the interface, then you would have always to write this, I don't know, 20 lines of code to get a scatter plot, which is annoying. So, and that's, as I said, I broke with the rule. And here you have one single mseries command, get scatter, and you get a scatter, and you get here the legend, and you get it colored, and as well, this function have a lot of, you can change your color map, you can move around your legend, and so on, but you can switch off the grid if you don't like grids. Yeah, but that's as well how you can generate these plots. Then another thing is the hex bin plot. So this is actually kind of showing the toxicity now. This shows the substrate and how it is in the domain where it is most dense. So, and we know all the contour plot, right? So this is kind of what Panda offers, but what Matplotlib really offers is much more crisp, and is what we usually use. And so there's as well a function to make this contour plot directly in PCDL implemented. So can't remember. Oh yeah, And then, of course, because it's Python, you can as well loop over the whole thing. And that's what I do here. So I loop over all the MCDS, I study a whole time series, I get out the cell count. So these are all my different cells and all the counts that I have over the whole time frame. Then I transpose the data frame and I can plot it. And you can see that your differentiated cell grow, and more or less all the macrophages and so on. The model setting are always 50. And you have some bacteria that get killed. And of course, you can as well, let you see a bit more. Look, J through, right? So it's very good to know all these parameters. So you can just log transform. So it's helpful to read these doc strings, and that's how you kind of on the fly manipulate your plot and analyze your data. And then there's the last plot that Panda offers is an area plot, just stacks up every one of the line in an area. I don't know if it's useful for us, but it's there. Here I have an example how to embed, and actually it's not anymore pandas plots, but because the PCL plots are in a way as panda plots are, you can use this AX equals AX function, and you can overlay. You should be able to overlay your toxin with your cells, and somehow it was erasing my cells somewhere in the code. As you can see, when I run this again, it's just blank. So that's why you cannot see anything here. Yeah, I don't know why this happens. I have to figure it out. It's somewhere, maybe a bug in my code. And then if you're familiar with matplotlib, it will be nothing special, but you can, of course, as well do the plot separate. So just two ways to show how you integrate your pandas or PCL plots into matplotlib for whatever you need it. Okay, so then finally, the last 3 minutes, we are here. We are in looking at ScanPy data, and here I do quickly a principal component analyzing using this on that object. I plot it. It's not colored here, but there is a way as well to, of course, color this. Let me see. And you can save these plots. Actually, they are saved a little bit on a special place. They always save the data to the figure directory, but I really have not time to go into this detail. But let me quickly show at least a little bit nicer version. So here, this is how you color them. So we see the cell types and the current phase from the PCD. Then, of course, we can do go to pre-processing neighbors. So we generate the next neighborhood network. Then we do Leiden clustering on the network, and we color by our Leiden clusters. It's maybe not so interesting for our data, but the wet lab biologists use actually these dimensional reduction techniques to figure out which cell type they have, because they know some gene expression, but they not directly know which cell type it is. But by us, it's different. We know which cell type we have, but still, it's good to know these dimensional reduction techniques. And then, of course, the same PCDL is, PCA is linear, and lately UMaps became very popular. So 2 lines of code, and you have the UMaps. T-SNE were popular before. So T-SNE is just trying to minimize the Kullback-Leibniz divergence. Then this is very information theory based. So some people came up with something called what was it? Force graphs, and it should preserve some things better than TCJ not does. So you get this plot there, and there are a variety of other dimensional reduction algorithm, and you just plug in the other name here, and you get the other plot out. Yes. My time is running out.
I was wondering if, let's leave a minute for questions. I propose that we leave a minute for questions. And then also we can definitely, have people reach out And I think perhaps there's so much material here, there could be room for a supplementary video or supplementary slides that could be possibly considered to be put in the workshop. Does that sound good to you, to take some questions and then consider that possibility?
I think I take questions, yeah.
Great.
Give me 1 minute to finish, a little bit summarize it. I will not run any other part.
Of course, yeah.
But so you do here the dimensional reduction. You can as well do dendrograms. You have the variety of all the plots that wet lab biologist knows, like heat map, cluster map. There are versions of these heat maps that are dot maps, violin plots, matrices. They all say the same story. It's just a different way to display it. You have a lot of information about cell differentiation, which is not important, not that important for us because we have this information. Gene expression data, how to normalize it. It's not data that we have. Then we can do spatial analysis. We can even do time analysis when you go down. We can study autocorrelation. We can look actually here, look which Python libraries you have used. And this is how, okay, this is how I want to show this one single plot. I want to show 2 more plots, please. So this is how you really analyze the whole time series, and you will get a U map on the whole time series, and you see how the cell types change over the time series. And then there is actually an own library, SquidPy, who only does analysis on spatial data. And I came to do some analysis, but it's a little bit more tricky, and PC Data Loader is not totally there to can do everything what is offered in SquidPy. But I managed to get into 3D data and you get T-stacks and you can study your 3D data. And there is a bunch more of libraries. So there is machine learning. There is actually image. You can directly integrate it with your image. You can integrate it with your, if you have X10 VSUM data, can directly bring everything into the same object. So I think it's really at the point where you can integrate your wet lab data with modeling data. Okay, and now I take question.
That's great.
Okay, where are we? Yeah. So please, I'm sorry for taking too much time.
Oh, it's no problem. If anyone has any questions, you're welcome to type it into the chat or just unmute yourself.
Where are we? I don't find my.
I have one quick question, Elmar. Maybe we'll leave it at that and then close. Well, first of all, there were some really beautiful plots, and it's really, really, I haven't seen this work much. It's really neat to see it come together and see this really great emerging tool coming out, and then the demo as well. I know how it could be useful for my work. So I'm really excited to work with it. If I was to go through that notebook, where would I want to put that notebook in order to get it to make it look like we had to make the data in order to interact, like we had to produce the data? Would I want to put that notebook into a PhysiCell directory?
Yes.
Does that make sense? Okay, great. So to get started running the notebook, we would grab the notebook, load it up, and put it in. We would put it into a PhysiCell directory, and from there, it looked to me like you would be able to then make the project and then run that data and produce plots similar to what you have. Correct?
Yes, exactly.
That's fantastic. Like I said, I look forward to doing that more, interacting with it more. That last section with all that spatial data looks like it's certainly its own section by itself.
Okay.
Almost.
Yes. So, other questions? Yeah. No. Okay.
Well, thanks for the great presentation, Elmar. I'm going to stop the recording.